Hello, my name is Zafar Zokirov and welcome to my thesis presentation. Topic of my thesis is the effect of smart heating control on drought in residential buildings, and the study was supervised by Professor Espoon Asunnot from Aalto University and advised by Sonny Salo from Capacity. The field study is part of the project Optimization of Inlet Water Temperature initiated by Espoon Asunnot and conducted by Capacity and Aalto University School of Engineering. The housing satisfaction level in Espoon Asunnot has decreased if implementing new heating control service by LeanHeat. The service adjusts the heating output according to the outdoor temperature and other external factors, for example, such as hourly price of district heating. The adjustment of inlet water temperature can lead to sudden changes in circulating water temperature, such as rapid drop in the flow temperature of heating network, which may lead to the drought. The main objective in this thesis was to conduct the field measurements and define the correlation between inlet water temperature and airflow velocity. Another objective of the thesis was to utilize comprehensive data analysis techniques to analyze data from measuring devices. To deal with this tasks, field measurements on thermal comfort were conducted, including temperature and air velocity measurements. On the basis of the received data from sensors, data analysis were performed. Data analysis consisted of data correction and visualization. To conclude findings from the field measurements, smoke tests was done. Also, in addition, an online survey on resident satisfaction levels were conducted during the measurements period. In the end, interviews from company representatives were taken to clarify and discuss the findings from the field measurements. During the study, several buildings were investigated, but in my case, I mainly focused on two buildings. Building 2 has a solid window view value. Ventilation type is mechanical exhaust and inlet. It was built in 1979 and renovated in 2014, while Building 1 has exhaust only mechanical ventilation with trickle vent. Windows U value is a bit worse than in Building 1, and building has gone through a lot of renovation work from 2004 to 2020. In this slide, you can see the example of a room setup for the measurements. Air velocity transducers are 1 meter away from the window. Surface temperature measuring thermocouples are installed on inlet and outlet radiator water pipe, on window surface, and also one on trickle vent to measure the inlet air temperature. Omnidirectional anemometers for air velocity are installed in this measuring mast on 4 different heights: 10, 60, 100 centimeters, and 1.7 meters. These sensors also measure temperature difference on different heights. For data analysis, I used Python. Data from sensor were not perfect and required some work on data cleaning. 10% of the highest peaks were removed and replaced by averaged values. In detail, peaks were replaced by calculating the absolute difference of the previous and the next data point, then taking the mean or minimum of both. Data sets with 15 and more missing data was considered as a corrupted, and it wasn't used in this thesis. Also, unfeasible peaks were removed and missing values were interpolated. For convenience, all the data sets were used in coordinated universal time format, and it was used as a default. Additional to the data from the sensors, I got some data from meteorological stations and LeanHeat's cloud. Okay, let's have a look at the findings from the measurements. While air velocity in Building 2 was smooth and within the standards, in Building 1 we can see some peaks and some particular pattern. If you look closely on one-day data, it's obvious there's 3 peaks per day, exact time for every day. It was later explained by kitchen hood fan boosting times. However, even most of the peaks were lower than acceptable limits, acceptable air velocities. when kitchen hood was turned off, air velocity was lower than 0.1 meter per second, which is also in acceptable limits. In this thesis, the effect of adjustable temperature on drought in residential buildings was studied by experiments and regression analysis. Regression analysis was used to identify and characterize relationships between data from air velocity measurements and temperature. Due to both temperature and airspeed being continuous variables and having a linear relationship based on time, linear regression would be the most applicable in this case. The first graph stands for indoor air temperature and air velocity. The second graph shows the correlation between inlet water temperature and air velocity. From these figures, we can assume that air and inlet water temperatures didn't have an impact on drought. Air velocity near the window were mostly uniform and independent from the temperature changes. During the smoke test, we had two cases. The first case when the radiator valve was fully closed and the radiator temperature was cold, surface temperature. And in second case, radiator thermostat valve was fully open with highest temperature set point possible. Case 1 and case 2 was performed consecutively, one by one, with 1 hour interval. Interval was needed to let the radiator warm up and reach maximum temperature conditions. Radiator temperature, surface temperature, and window surface temperature was measured during the experiment. Crucial moments from the taken videos were shown as a sequence of snapshots presented in this slide. As a result from the test, we can say that when the radiator was turned off, it led to serious down drought from the window. In comparison, in second case, with the high temperature set point, the warm window surface prevented developing any downdraft from cold window. In terms of sensation of the drought, the flow caused by warm window temperature and the hot radiator had relatively small velocity and warmer temperature, which is less likely to cause any drought. However, when the surface temperature is very cold and radiator is cold, it might increase the risk of the drought in the apartment. This slide shows the percentage of dissatisfaction of the residents during the periods, baseline and intervention. So if air velocities were in acceptable limits, why might people still be dissatisfied? In my opinion, one of the reasons might be the large temperature fluctuations in different parts of the room. From temperature measurements, it was seen that difference was 2-3 degrees, which is common for naturally ventilated apartments. To dig deeper in this topic, a couple of interviews were taken from fromLeanheat and Espoon Asunnot company representatives. First, specialists were asked to briefly discuss the findings from the study and provide some insights from the company point of view. Also, questions were asked on company's plans and improving indoor environment comfort and developing smart heating control systems. They shared some concepts they are working right now. For example, fromLeanheat shared the concept of smart ventilation system. Regarding the building 1, it seems to be a problematic issue for many years. Smart heating system was implemented in 2016, and since then, many renovation works took place in the building. However, satisfaction levels remain slow. From a discussion, I should mention that the smart heating system algorithm has introduced new constraints. For example, it can't let temperature go lower than 21 degrees, and also water temperature changes must be gradual to avoid rapid temperature spikes to avoid drought. Also, company representatives claims that overall satisfaction level are higher than average, like about 3.5 from 5, and building 1 is spoiling the stats. In conclusion, I should say that field measurements and data analysis were successfully conducted, and the main question of the thesis was answered. With the current smart heating control algorithm setup and water temperature set points, it can be assumed that drought was not caused by adjustable inlet water temperature. However, housing satisfaction levels were extremely low and people still complain about the drought. In my opinion, it might be caused by large temperature asymmetry. However, it can't be assumed for sure and it requires further investigation. I appreciate your attention, and if you have any questions, please feel free to ask them in the comments.